First part of question 1 asks you to define the density of material. So make sure that you do give a proper definition. Don't just waffle about it, give the precise definition. Sort of definition that you should have in your notes and that will be in the book. Like in the chapter on density, for instance. If you think that physics is all about having a formula, bunging the numbers in and getting an answer out, you'll probably find part B quite complicated. But if you're prepared to sort of stop and take your time and think about it, and work out what all the simple stages are, and explain as you're going along what you're doing at each stage, it is actually quite straightforward. So look at the important information that's given. We're told that we're trying to make a rod of brass of volume 0.80 times 10 to the minus 3 metres cubed. And we're told that 70% of the volume of brass is copper. So the first thing I would do is I would say, well, if that's the total volume of brass, and 70% of the volume is copper, I'd work out what volume of copper we need to use. And I would write that down, the volume of copper is whatever. And then, when I know the volume of copper, and I know the density of copper, I'm able to find the mass of copper. And then I can repeat the process for the zinc. We know that 30% of this total volume is zinc. So I can find the volume of zinc, I know the density of zinc, so I can find the mass of zinc. And I write that down and explain what I'm doing, explain that I'm finding the volume of zinc, and then finding the mass of zinc. Through the last part, if I've worked out what mass of copper I've used, and I've worked out what mass of zinc I've used, then I've worked out the total mass of the brass. And since we know the volume of the brass, we know the volume and we know the mass, then we can find the density. Question 2 is about finding the energy stored in a spring. Now remember, in an exam you'd have your data sheet available with the formulas on, so let's have a quick look at the formulas that are there. Can we find a formula for the energy stored in a spring? And we can, it's this one here. Energy is a half force times the change in length. Very important to remember that the half's there. So if we come back to the question, we found the formula for the data sheet, which you'd have that with you in the exam. So to find the energy stored, half times the force times the change in length. So we look, does it tell us what the force in the spring is? Well, it doesn't, but it does tell us the mass of the lorry. So if that's the mass of the lorry that's sitting on top of the spring, you should be able to work out what's the force that's pushing down on the spring and squashing it. And then the question does tell you directly how much the spring compresses, so that's the change in length. So with that information, finding the force and then using the change in length, using the formula, should be straightforward to calculate the energy stored in the spring. The first part of question 3 is quite straightforward. Notice that there's 8 marks available for 4 answers, so in each case you've got to give the answer, which is X or Y, and then with the reason. So it's really important that you do put the reason in. Let's say for part 3 where you've got to spot which material is ductile, even the one that's ductile isn't very ductile. To do part B, it's probably worth looking at the data sheet because it mentions Young modulus, and if you're not sure what Young modulus means, look at the data sheet, and the formula it gives on the data sheet is that Young modulus equals, well, the sheet says it's tensile stress divided by tensile strain, and then the data sheet actually makes things simple for you, because to save you having to work out stress and strain, it puts the things in, puts everything in that you need to know. FL divided by A times delta L. And in this question, we're asked to find the tension in the cord. So look at this formula, the tension, that's the pulling force, so that's F. So, do we know the Young's modulus? Yes, it's given in the question. Do we know the cross-sectional area? Yes, it's given in the question. Do we know the original length, the unstretched length? Yes, it's given in the question. Do we know the change in length? Well, for that we've got to be careful, because the question doesn't tell you directly what the change in length is. It tells you what the length is when it isn't stretched, and it tells you what the length is when it is stretched. So from those two things, you can easily find out the change in length. Now the other thing to be careful of in this question is the units. The area is given in millimetres squared. If I was doing that, I would convert that to metres squared. Because the Young modulus, well, look, it's given in pascals, but pascals are newtons per metre squared. So we've already got metres squared as the units part of Young modulus, so that's why it makes sense to put the area into metres squared as well. We've got everything we need to know to put in the equation to rearrange to find F, the tension, and then the next part of the question, to calculate the energy stored. Well, just like the previous question, when something is stretched, the energy stored is that formula that's on the data sheet, half force times change in length. So if you've found the tension and you know the change in length, you can find the energy stored.